Okay, we're going to take a brief moment just to discuss something that's not clearly explained in the book. So today we're going to look at basically dose response curves and the way that toxicologists determine what the threshold level of toxicity is. So basically, a lot of chemical manufacturers believe that they should not be held responsible for any harm. They're innocent until proven guilty. And the scientific community takes the precautionary principle and they say, you know what? Well, if you aren't sure if it's going to hurt you or not, then why take the risk, right? So basically, a lot of new age pharmaceuticals, chemical manufacturers, everything from battery manufacturers right to painkillers, they say that the precautionary principle costs them more money and it's limiting getting new products out on the market. But of course, no one would want to have a serious implication happen to them or become hurt by some of these things as technology rolls out new products. So we use what's called a dose response curve, and when we talk about dose response curves, we either have LD50s, which are the lethal dose that kills 50% of the population, LC50, which is lethal concentration for like gases and liquids that kill 50% of the population, or ED50. ED50 is the effective dose where 50% of the population feels an effect, right? So we could take something like Advil, right? Ibuprofen, for example. Well, how many people would have to take one pill to feel an effect? Well, that would be the ED50 dose. And on the back of the bottle, that usually is about 200 milligrams. So that's why on the back of the bottle it says, if you take one pill, you might feel better. And if you don't feel better after a little while, you can take a second one, right? That's because 50% of the population is going to have an effective dose after one pill. The other 50% is going to have to take two. But when we talk about LD50, how many people would have to take a pill in order to have 50% of the population perish, right? So that would be people taking, obviously a tremendous amount of medication, in order to kill them. So we always are looking at dose response curves. And so we're trying to use more humane methods of testing, but basically we start off with lab rats and mice and move to larger animals like rabbits and then even primates. We're trying to find other replacements for animals. My grandfather actually used to raise hundreds of rabbits for a local laboratory, Thor Labs, in the 1970s, and he would sell them. Farmers did this around here. It was very common. But obviously, we don't want to be, killing animals, but it's really in the interest of better human life, right? And they do even testing on cosmetics, right, to find out if a cosmetic can be applied safely. So we're trying to look at other ways to protect animals and still get the results that we want, right? Looking at chicken eggs and tissue cultures and computer simulations, right? So this is a typical LD50 curve. We'll practice making this in class on the handout. And you can see that the LD50 is the dose that kills 50% of the population, right? Now, this graph I don't really like entirely because the bottom is a little bit inaccurate. Most toxicologists will actually use a semi-logarithmic graph where each number down here at the bottom, these numbers right here, should go up. Instead of being linear, this should be a logarithmic scale. I really do believe that is poorly portrayed by the book. But the curve is the correct shape. It's a S curve usually, but usually you'll see that this guy right here will be 1, and this guy right here will be 10, and this guy right here will be 100. And so that's the way we practice it in class, right? So here goes a couple of average toxic ratings for different substances, common substances, some of them that you'll be familiar with, right? And so here on this graph, I've shown you a nonlinear and a linear dose response curve, right? So there's a couple of key terms here. On this guy right here, I drew in a logarithmic scale to show you what it should look like. And that's the graph on the left I'm talking about right now. This is a nonlinear dose response. This is most common. And the nice thing about this is as I administer a dose here and here and here, right? What happens is I can administer 1, 2, 3. I'm not getting a very big effect in the beginning. So it's not very toxic, actually, in the beginning, this substance on the left. It gets more toxic rapidly as I move through this area right here. Okay? So in this case, this substance right here is more toxic at higher doses, except we have to consider this. In this case, there's no threshold level of toxicity, which means that even at the very lowest doses, there's going to be a response. But then that response stays pretty constant until we get to a higher number. I would say ibuprofen probably follows that curve, right? Because most people get a response after 1 pill. 2 pills, 3 pills, women that have just had childbirth, they give them doses of 8 pills at a time. And you shouldn't do that every day, but they do it, right? So that kind of illustrates that we don't see much more response throughout this whole region, and then rapidly you would see something terrible happen if you continue to administer more medication, right? Over here, in the one on the right, this guy shows that there is a threshold level of toxicity, and it's at this value, whatever that hypothetical value is, right there. So, in that case, no response at all. You could be exposed to this in low doses with absolutely no implication whatsoever. Let's take something, right, like vitamin C, right? It would take a lot to overdose on vitamin C, and so you could take a lot of vitamin C, and then eventually you would have some kind of threshold level where you wouldn't want to eat a whole bottle of vitamin C. But in this case, this is a linear response curve, and because of this blue line over here on the left, right? That blue line on the left, right there, this guy, and this guy over here on the right, those are both linear response curves. If that's a logarithmic scale at the bottom, that is actually showing a logarithmic response. The effect is going up much faster than it would on a semi-logarithmic graph. So those dashed lines indicate to you that this potential poison, chemical, whatever it is much more powerful than something that shows the S-curve. Okay, so they also mention this therapeutic index of a drug. And the therapeutic index of a drug is nothing more than the ratio, last point here, of the ED50 ratio over the LD50. What that is saying is, what's the dose that I have to give somebody in order for them to see a response over what's the dose that I would have to give somebody in order for them to perish, or 50% of them to perish, right? So if this number here is very low, let's say it's ibuprofen, right? 200 milligrams. And let's say that the dose that kills a lot of people for ibuprofen may be at a very high number. Let's say that number is 10,000 milligrams. Right? I get some ratio from that, right? And that ratio really is going to be 200ths, okay? Or 0.2%. If I have a number where these two are closer together, that number is going to be higher, and we have to be very careful with the way that we use drugs like that, right? So that's what the therapeutic index of a drug actually is. Okay, that's it for now.